Officer in the Space Science Advancement Unit. My academic background is in Geography and Environmental Studies. I completed my undergraduate at the University of the Western Cape and my honours at Stellenbosch University. This is my partner, Dr. Pierre, and he will introduce himself.
Hi learners, my name is Pierre Sillier. I am an engineer. I have worked here at Sansa Space Science since 2014 as a research physicist. My background is in electrical and electronic engineering, and I am delighted to share this exciting experiment on Snell's Law with you today with the assistance of my teammate Hazel Ann.
Okay, so today we're going to be talking about and demonstrating Snell's Law, or the law of refraction. Refraction refers to the change in speed of light as it travels from one medium to another. Today, we are going to be measuring how much light refracts or bends when passing through a less dense to a more dense medium by the demonstration of Snell's Law. Our aim is to determine the refractive index of unknown materials using Snell's Law, which states that N1 sin theta is equal to N2 sin theta 2, where N1 is the refractive index of material 1, N2 is the refractive index of material 2. Theta 1 is the angle of incidence and theta 2 is the angle of refraction. Pierre will now be demonstrating our setup as well as the actual demonstration of Snell's Law using different mediums and materials.
Learners, you have probably seen when you put a stick or a straw into a glass of water, it seems like the stick suddenly gets a bend when it goes right into the water. That is due to the refraction of light at the surface between the air and the water. And the law that describes this refraction is exactly Snell's Law. So today we are going to demonstrate Snell's Law and use Snell's Law to determine the refractive index of three different media that are denser than air. Thanks, Hazel Ann. The materials that we will be investigating today is plastic, glass, and water. The light source that we will be using is a green laser beam that we will shine through each of these media, and we will then determine the angle of incidence by having marked the angles of incidence from 20 degrees, 30 degrees, 40 degrees, 50 degrees, 60 degrees, and in each case we will observe the direction of the beam through the medium, and from the point of incidence to the point of exit determine the direction of the beam when it travels in that denser medium and calculate from that the refractive index. We will start with the plastic. This is theta 1, our angle of incidence. This is the normal on the surface of the plastic. When we have an angle of incidence that's 0, the beam goes straight through without any bending. As we advance that angle of incidence, we will find that more and more of the refraction takes place. So we will start off with an incidence angle of 20 degrees and access the beam at the glass at exactly the same point and marks the exit point from the plastic. Next we do 30 degrees and 40 degrees and let's get it right, 50 degrees 60 degrees. We are moved to slightly, just so that the exit point is still can be marked. Good. So next then we will measure, draw a straight line through each of those. You can draw that one. That's for our 20 degrees incidence. And we do 30 degrees incidence. (40 degrees incidence angle), 50 degrees, and 60 degrees. And we'll measure each of these angles, and you can measure those from. So for the 20 degrees incidence, the angle of refraction was 10 degrees. Can you write those down for us, please? Or you're going to write them down. Thanks, Aslan. Okay, so Aslan will write down these angles as we measure them. So when we had a 20 degree incidence angle, our angle of refraction was 10 degrees. When we had a 30 degrees incidence angle, our angle of refraction was 19.5. With 40 degrees in, our angle of refraction was 24. For 50 degrees in, the angle of refraction was 28, Aslan. And for 60 degrees incidence angle, our angle of refraction was 32 degrees. And those were our measurements for the plastic. We will now repeat the same exercise for the glass. So far was for 3 different media. We have recorded the incidence angle theta 1 and the angle of refraction theta 2. And for air, the refraction index is 1. So we can calculate the refractive index N2 of the medium by rewriting this equation of Snell's law in the following form. We can write it as sine of theta 1 divided by sine of theta 2, because N1 is exactly 1. So we have now recorded a number of incidence angles theta 1 for the different materials, and we have recorded the refractive angle theta 2 for each of these materials, and we will calculate the N2 value from the average over all these different incidence angles. Good. What we have done so far was to have an incidence from air into a more dense medium such as glass or plastic or water. It is more difficult to do the experiment to have the light source inside the denser medium and then look at the refractive angle in air. But in the case of going from a more dense medium to a less dense medium, the bending will be away from the normal. So in the case of going from glass to air, there is an angle at which the bending angle will be exactly 90 degrees, and after that we will have total internal reflection. This angle of incidence for total internal reflection in the case of glass is 41 degrees. So if we would have a light beam inside the glass that strikes the interface between the air and the glass with an incidence angle of anything larger than 41 degrees, there will be a reflection of that wave back into the glass, and the reflection will continue. And so this is the principle of operation of optic fibers. The light is shone in at the entrance of the optic fiber, and it bounces back and forth inside the optic fiber, even if this optic fiber is bent. Because an optic fiber is a very thin cylinder of glass that can be bent and that can carry light over long distances without a loss, with very little loss. And so optic fibers are used these days for internet communications and for many other opportunities when we want to convey light around a bend by confining the light to the inside of an optic fiber. One of the applications of optic fibers is in endoscopy. In an endoscope, people use the optic fiber to see inside the body. So the light that is observed is reflected from organs inside the body that are illuminated through an optic fiber, and then the reflection from that optic fiber conveys the image from inside the body to the eye of the physician who is doing this endoscopic observation. I'm going to illustrate the case of total internal reflection with the following setup using a prism. Instead of having two parallel surfaces, we will now have two surfaces with a 45-degree angle between these two. So when the light goes into this medium, it hits that second surface with an angle that is closer to the total internal reflection angle. So initially you could see that the light is coming out of this surface and hitting the ruler. And as I increase the angle of incidence, then at a point the light disappears and no longer is exits into the air. And what actually then happens, it travels inside this medium, gets reflected off this surface again, and we can see it at this point. So if I go back and just decrease the angle of incidence again, you see it disappears from here, and we can see it over there. So you can imagine that this surface is the outer surface of an optic fiber, and so if the light is coming in at more than 41 degrees, we get the total internal reflection, and the light bounces back and forth. So this screenshot now shows you the values of the incidence angles and refractive angles that we've recorded, as well as the average value of the refractive index for each of these materials we calculated from our experiment.
Okay, so this is a piece of optic fiber and we have a light source, and I'm going to switch the light source on. Okay, and so this is demonstrating what Pierre has just explained of the point of total internal reflection. So we have the optic fiber, we have the light traveling through the optic fiber, and the light is traveling and it's coming in at an angle, it reaches total internal reflection and it reflects again. So the reflection does a zigzag within the fiber, and so the light does not escape. And so here you can see the light running through the optic fiber.
We will address some of the questions that may arise from this experiment now. Aislan, can you tell me, why does the light bend when it seems to, why does the light seem to bend when it goes from a less dense medium to a more dense medium?
Okay, so light bends, changes angles or direction due to the change in the speed of light. For example, as we demonstrated, when light travels from air into water, it slows down, causing it to continue to travel at a different angle or direction.
And does it make a difference whether we would use a white light source or a laser beam as the source for this experiment?
Okay, it does make a difference because light of different colors have different wavelengths and will slightly affect the indices of refraction.
Thank you. Okay, and then last question. Hazel, and how does the density of the medium affect the refraction?
Okay, so the density affects refraction because the denser the material, the higher the refraction index.
Oh, and that means that the velocity is lower in the denser medium.
That's correct.
And the refractive index is the velocity of light divided by the velocity of the light in the denser medium.
That is correct. I will now ask Pierre a few questions just to clear up any uncertainty you guys may have. Okay, so Pierre, how can I remember whether refraction is towards or away from the normal when the light goes from a denser or from a less denser to a denser medium?
And I think the easiest way to remember that one is to remember the optic fiber. In the case of the optic fiber, the light goes from a more dense medium to a less dense medium if it would exit the optic fiber. Mm-hmm. But it does not. Yes. And so the refraction has to be away from the normal in order for total internal reflection to take place. So if you can remember, in optic fibers, I'm going from a more dense medium glass to a less dense medium air, and the refraction is away from the normal. In the case of going from a less dense medium air into a more dense medium, the opposite happens and the refraction is towards the normal.
Okay, so how is Snell's law applied in technology?
Good question, Hazel Ann. Snell's law determines how optic fibers work. And nowadays we have optic fibers used for many applications, primarily in communications, but also for seeing around corners, because we can use an optic fiber to take light from another place to where you are and have the light travel around a bend if we have an optic fiber guiding that. This application is used in medicine, in endoscopy, where we want to see inside the body. So they insert an optic fibre, send some light through the fibre to the place they want to observe inside the body, and with another optic fibre they take the image back outside so the physician can see what it looks like inside the body without having to open up the body except for a small little hole.
And Pierre, my last question to you is, for which careers do I need to understand Snell's Law?
Ladies and gentlemen, if you are going to study engineering or electronic technician or any field where you want to be involved in communications, these days you need to understand optic fibers and Snell's Law and how it applies. However, Snell's Law applies in any situation when we have light going from a more dense medium to a less dense medium or vice versa. So the whole field of optics and astronomy and lenses, and if you become an optician that has to make measurements for people's refractive indices and what lens would do the right correction for their vision, you need to understand Snell's Law.
Okay, so there you have it, grade 11s. This is our demonstration of Snell's Law. We hope that you learned a lot and that you also try and do this experiment at home.